everyone, I am Satya. Today our group will be discussing self-healing mechanisms for microservices in cloud environments. In simple terms, this means how modern software systems can automatically detect problems and recover without always waiting for a human engineer. This topic matters because many of the apps we use every day, such as online shopping apps, banking systems, and the streaming platforms, run in the cloud. Instead of being built as one large application, they are usually divided into many smaller services called microservices. Each microservice has a specific job, such as login, payments, or notifications. In practice, these services are often packaged using Docker and managed by platforms like Kubernetes. This design makes software easier to scale and update, but it also increases the chance of failure because many small parts are connected. If one service fails, it can affect the rest of the system. In older systems, engineers had to manually detect and fix these issues, but in modern cloud systems, this is often too slow. That is why self-healing is important. A self-healing system can detect a failure and automatically restart or replace the affected service before users are seriously impacted. So the main focus of our presentation is simple. How can cloud-based software stay reliable even when failure happens? With that introduction, I will now hand it over to the next speaker who will explain the evidence and practical background behind this topic.
Hello, I'm Sanjeev Adhikari. Now that we have introduced the topic, I will talk about the evidence and real-world context behind it. One important point in both research and industry is that in large cloud systems, failures are normal. Services can crash, servers can become overloaded, networks can slow down, and user traffic can suddenly increase. Because microservices are connected, even a small issue in one service can sometimes affect other services as well. This is why companies rely on monitoring and visibility tools. For example, Prometheus is commonly used to collect system health data like response time, CPU usage, memory usage, and error rates. Grafana is then used to display those information on dashboard so teams can quickly understand what is happening. So when we say the system detects a problem, tools like these are often doing that work in the background. Another key point is that companies are moving from manual recovery to automated recovery. Instead of waiting for engineers to detect and fix every issue, many teams use automation tools like Jenkins in CI/CD pipeline to support reliable deployment, testing, and faster recovery. A well-known example is Netflix, which intentionally tests failures to make sure its systems can recover automatically. So, overall, the evidence shows three things. Failure in cloud systems happen regularly, manual recovery is often too slow, and tools like Prometheus, Grafana, Jenkins, and cloud automation platforms are now essential for reliability. Now that we understand why this topic matters, the next speaker will explain how self-healing actually works in practice.
Thank you. I'm Sandeep Adhikari. In this section, I will explain how self-healing works in a simple and practical way. The easiest way to understand self-healing as three-step process: detection, diagnosis, and recovery. The first step is detection. Before the system can fix anything, it has to notice that something is wrong. In cloud environment, tools like Prometheus continuously monitor microservices by checking response time, error rates, and availability. If a service stops responding or becomes unstable, the system can quickly detect it. The second step is diagnosis. After detecting the issue, the system tries to understand what's happening. For example, it might identify the container crashed, memory usage become too high, or the service is receiving too much traffic. The third step is recovery. This is where the tools like Kubernetes plays a major role. Kubernetes can automatically restart a failed container, replace it with the healthy one, or launch extra services instant if demand increases. If traffic routing is the issue, tools like Istio can redirect user away from unhealthy services and send them to healthy ones. Compared to traditional systems where the engineer receives an alert and fix the problem manually, self-healing system responds much faster. This means less downtime, fewer interruptions, and better reliability. So the key takeaway is that self-healing helps to software recovery quick and continue working even when problem happens. With that in mind, I will now hand over to the next speaker who will explain why this matters in real software engineering practice.
Thank you. I'm Sandeep Bhattrai. Now I'll briefly explain why self-healing systems are important in real-world applications. The biggest benefit is reliability. Reliability means the software continue to even work when something goes wrong. For users, this means fewer crashes, fewer interruptions, and a smoother experience. For example, if someone is making an online payment or watching a movie, the system can recover in the background before the user can even notice a failure. Another important benefit is reduced downtime. Downtime is when a server becomes unavailable or unstable. For businesses, even a short outage can cause lost revenue, frustrate users, and reduce trust. Technologies such as Kubernetes help reduce downtime because they can automatically restart failed services much faster than a human team. Self-healing system also reduce pressure on engineering teams. With monitoring tools like Prometheus and Grafana along with automation tools like Jenkins, many routing issues can be detected and handled automatically. This allows engineers to spend more time improving the product rather than constantly fixing problems. From a software engineering point of view, this also changes how systems are designed. Developers now assume that failure will happen, so they design systems that are easier to monitor, restart, and recover. In other words, resilience becomes a key part of the system design. With that, I will now hand it to our final speaker who will discuss the future of self-healing systems and the challenges that still remain.
Thank you. My name is Dwal Krishna. In this final section, I will briefly talk about the future of self-healing systems and some remaining challenges. Today, many cloud systems can already react automatically after a failure happens. For example, Kubernetes can restart failed containers, and cloud providers like AWS, Azure, and Google Clouds support recovery through features like auto-scaling, health checks, and monitoring. In the future, self-healing is expected to become more proactive instead of only reactive. Right now, many systems act after something fails. But with artificial intelligence and predictive analytics, future systems may detect warning signs earlier and take action before users are affected. At the same time, there are still challenges. Modern applications can have hundreds of microservices, which makes it harder to find the exact cause of a problem. Also, if an automated system makes the wrong decision, it could make the issue worse. So even with advanced tools, careful design, testing, and human oversight are still important. To conclude, self-healing mechanisms are becoming essential because modern cloud applications are too complex to rely only on manual fixes. By using tools like Docker, Kubernetes, Prometheus, Grafana, and Jenkins, software teams can build systems that recover faster, reduce downtime, and provide a more stable user experience. Thank you very much for listening.